Thank you very much. Hi, nice to meet you. Hello, good afternoon, good morning, good evening. My name is Thomas Irmscher. I work for ETAS GmbH, located in Munich. I'm a product manager for security testing services, and I have now around 15 years in cybersecurity. Of that, around 6 years in automotive cybersecurity, worked in several customer projects for automotive cybersecurity worldwide. Yeah, nice to be here. Hope to give you really a good session today and hand over to Marcus.
Hello, everyone. Thanks for your time. Thanks, Thomas. My name is Marcus Cardoso. I'm product manager at ETAS for a protocol fuzzing tool called CycleFuzz. Quick background, I work since 2004 in the test and measurement industry, most focused on the automotive, mailing products in the market of Latin America with hardware in the loop, software in the loop applications. I also endeavored myself 3 years in the startup world on the B2B tech companies. And currently I'm product manager at ETAS, globally responsible for this product. Thank you very much. Welcome. And Thomas is with you.
Hey, thank you. So here we see an overview of our webinar, respectively the goals we would like to set for today. First goal of this webinar will be that you, after this webinar, can understand what is fuzzing, what is the relevancy of fuzzing in current automotive cybersecurity validation verification processes, what are the backgrounds, what are the regulations behind it, why are we doing this. Second goal will be that you understand what are the different fuzz testing techniques, what kind of fuzzing methods are there, which types of testing, for example, black box, white box testing. And one very important part will also be here to see the difference between source code and protocol fuzzing. The third goal is then focusing on automotive. So what are the automotive peculiarities in fuzzing? As you may know, automotive is always a little bit different from enterprise IT and other areas. In this part, we will show you what kind of, let's say, requirements poses automotive towards fuzzing and how can fuzzing solve the one or other automotive challenge. And finally, you will also see some use cases from real automotive world to understand where can fuzzing be used with special regards to protocol fuzzing, in which situation it can be used and where it does make sense. Okay, then let's go directly into the topic. Start with the global regulation for fuzz testing. So I'm pretty sure I'm pretty sure that you are aware of all those regulations which were introduced in the recent years. Very predominantly at this point is the UNR regulation 155, so for cybersecurity management systems, and also the UNR regulation 156 for software update management systems. So these are really mandatory norms, especially for EU market, but also for South Korea and Japan. That means all the car makers who want to sell their cars in the UNR affected countries have to fulfill cybersecurity testing, cybersecurity validation. And we will see also that fuzzing is one puzzle piece to this fulfillment. Beside the UNR regulation, there are also other, let's say, legislation or guidelines available. For example, in China, you have the GB and GBT standards. Here we have not the UNR affected. However, the GB and GBTs, they are quite similar and put quite similar requirements also to the car makers. There are also a bunch of regional guidelines available, for example, in Japan with JESPAR, or in the US with the NHTSA cybersecurity best practices. One very specific norm I would like to highlight, which is very, very well known, is the ISO 21434. And we will also have a look in the next slide on this. So the ISO 21434 is finally, so to say, the handbook for an automotive cybersecurity engineer to design and engineer road vehicles carefully, how to, let's say, develop according to cybersecurity goals, And also finally, it shows how to integrate cybersecurity and also to verify and validate it. Let me show you one aspect here. So we have this requirement 11, which is in clause 11, cybersecurity validation, and it says validation activities at the vehicle level have to be done to show the adequacy achievement and of cybersecurity goals. One moment. The ISO 21444 goes not really into the details. It says, for example, you must do testing. Yeah, you should do it. However, it does not really recommend concrete techniques. That means testing should be done, and the method is more or less open. That means fuzzing is here recommended as a concrete technique, but not really prescribed. Then I would like to hand over to Markus for giving you an overview what is cybersecurity verification and validation for vehicles.
Sure. So let's start what is fuzzing technique itself. So the technique means that we have a target, and in this target we send a series of inputs randomly generated, and we check for this the status of this target. We check how this target responds. So we call random or pseudo randomly generated because what is really most of the value of a fuzzing tool is that we generate the random messages in a certain way, targeting some areas of the software. For instance, I can target the UDS, I can target the other like the UDS or non-UDS messages and etc. So the goal of fuzzing is to ensure software robustness and find weaknesses. So there are basically three types of testing of fuzz testing. One is called black box testing. So in the black box testing, I have no information about the target. So basically what I have is target as a black box, and I send information without having I send the random message without having information of the target. For instance, I don't know the software that is there, or what are the UDS services if I'm talking about protocol fuzzing, for instance. This is the black box testing. The gray box fuzzing, I have some information about the target. So it's a combination between what we call white box and black box. And in the case of gray box, I may have some basic knowledge or basic documentation about the target. And when we talk about white box fuzzing, I have fully control and fully access to the documentation of the target. So the difference here in the white box is that I can really create even instrumentation in my source code to check the reaction of my target. When you talk about when these tests are used, black box fuzzing is basically used in more explorative tests. Gray box and white box can also be used in functional and explorative tests.
Thank you very much, Markus. So I will now give you an overview where to apply fuzzing along the cybersecurity development and verification validation phases. That means you see here the V model showing a little bit the structural flow of the ISO 21444. That means on the left side, starting with the concept design phase, then doing the code and build phase. And finally, on the right side, you see the verification validation phase. You can also see on that slide that fuzzing can really apply in various stages. For example, directly after the code and build phase, you have the source code of the software. And here you can apply the so-called source code fuzzing. That means fuzzing of concrete code modules, functions, or executables. In the next step, or let's say in one level higher, on the component or subsystem level, you can apply protocol fuzzing, for example, beside other testing techniques like penetration testing, functional testing. And finally, it's also possible, if you have the right tools, you can also apply protocol fuzzing to a full vehicle, so to a full system. If you then look on this or at this full vehicle system level, there are various protocols, interfaces, and aspects you can fuzz test. So you see here the vehicle showing its various interfaces, like wireless interfaces and also wired interfaces. We structure here the ways of fuzzing in 3 levels. So first, with the wireless interfaces, in modern cars you have Wi-Fi is activated or Bluetooth low energy communication links, and you can, if you have the right tools or the right fuzzing lips for that, fuzz also Wi-Fi networks and communication links. Another aspect would be to fuzz then on the wired level. That means the physical connections inside the car. One example here is the OBD connection, where you can get, let's say, public access to the car network, to the vehicle bus. And a third aspect will be then also focusing on this wired interfaces to the closed wired. That means there is, you for sure notice, the car consists of several CAN buses, CAN FD or Ethernet communications inside. And the way would be then opening a wired connection, for example, opening a hatch and then tapping to the connection to the bus and put some fuzzing message on the bus directly. Okay, so that we have now understood where to apply fuzzing along the vehicle development process, we are now going into the topic of the different fuzzing techniques. So especially focusing on source code versus protocol fuzzing. We start with source code fuzzing. Here on this picture, you see the overall setup. Marcos already introduced that a fuzzing setup always consists of a fuzzer that creates the test cases, the fuzzing test cases or the fuzzing messages, and also a target. And the main thing, well, let's say there are 2 very important aspects if you're doing fuzzing. The fuzzer first needs to create the messages and the test cases which are executed on the target. And the second important aspect is you have to monitor the reaction of the target. And as Marcos already introduced, there are several ways or types of testing. One part is, for example, white box testing, which means you have direct access to the source code. And what you see here is source code fuzzing, where you need to have direct access to the source code because you need to implement and add additional components. So beside the original source code, you also need to implement sanitizers and the so-called fuzz stub. So the fuzz stub is, let's say, the relevancy of the fuzz stub is to execute then the test cases or the generated test cases that they can be executed in the source code or on the basis of the source code. And secondly, you also need the sanitizer to make any reactions of the target visible. That means if you, for example, execute then the fuzz test cases in the source code, for example, that you generate certain input to a function, you need to make sure that you can measure or monitor the reaction of the target. And sometimes if a fuzz test case is being executed, you cannot really see does the program behave correctly or does it have problems? Is it crashing currently or is it not reacting at all? And you need to visualize this. And for this, you need the sanitizers. So with sanitizers, you can make clearly visible if a program, for example, crashes, that you can later on monitor with the fuzzer the reaction. If you put all those components together, then you need a certain, let's say, tool or compiler to create this compile program, which will then be executed. So for source code fuzzing, why are you doing this? Or basically, what are typical errors which you can find with source code fuzzing? For example, buffer overflows, uncaught exceptions or null pointer crashes, infinite loops, and memory leaks. These are typical errors which you can find with source code fuzzing. What are ideal targets, or where does it make sense to apply source code fuzzing? This is everywhere basically where you have a large variety of inputs to a certain system. For example, if you have a parser. A parser takes input and then goes over that input and parses it. And here fuzzing really makes sense because there's a huge variety of things which can go wrong. And if you are applying source code fuzzing, the chances and the likelihood is very high that you hit the one or other bug and bring the program crashing. Other things are any kind of applications where you have an UI to the user, for example, browsers, any kind of frontends, and also interpreters and databases are well-known targets for source code fuzzing. With that, I hand over to Markus for the aspect of protocol fuzzing.
Super. Thank you very much, Thomas. So Thomas just showed to us what is the concept of source code fuzzing. That basically we have the source code and we start generating these random messages in the input of the source code, and we analyze the response through the sanitizers, right? Now, what is the concept of protocol fuzzing? Protocol fuzzing, I also generate several inputs for a certain target, but I send these inputs through the bus of this target. So how does it actually work? What is the anatomy of a protocol fuzzing setup? I have here several test cases that are generated randomly or pseudo-randomly, meaning I can generate it if certain boundary conditions are fully random, and I send these test cases to the fuzzer. It's very common that the fuzzer itself, it generates test cases, and one of the quality of a fuzzer is measured according to how random this test case can be generated, what are the configurability of the boundary conditions for my test case generation. And yeah, so the flexibility on how I can generate these test cases is one of the main, let's say, ways to decide if it's a good fuzzer or not. So once I have my test case generated and I have my fuzzer, this messages, this test case, they are sent towards the target. And the interface with the target can be different ones. Can be over CAN, can be over automotive Ethernet, for instance. There are several options. And then what happens, I send a test case, this message randomly generated to the target. And then the target may have maybe an ECU with some REST bus or an ECU with sensor and hardware connected. I'm going to deep dive a bit more in typical types of target, but so far I'll keep here. I send the target and I monitor the reaction of the target. Once I monitor the reaction, I send this reaction back to the fuzzer as a health status check, and I see if the target crashed or not. Yeah, there are several ways that you can check the health of a certain target. One of the ways is over instrumentation message, meaning I send my mutated message, my test case, to the target, and afterwards I send an instrumentation message to check if the target is responding. If the target responds, it passed. If the target does not respond, then I need to handle this. May happen that after several trials to communicate with the target, I need to reset the target, or maybe I just monitor, for instance, the power consumption of the target if certain test case changes some difference in the power consumption. But this is the concept. I send test case to the target through the bus, and I monitor the health and the reaction of the target. And I do this thousands of times, and in some cases, millions of times. Okay, so this is the concept of protocol fuzzing. And when protocol fuzzing is when it's used, so what type of errors is found in general in a protocol fuzzing? It's very common that I discover unspecified UDS services. For instance, UDS services that doesn't exist, but then I send a CAN message in the format of a UDS service. in an ID that doesn't exist, and may happen the target response. If that happens, this is an issue. Or unexpected denial of service from the target, or the target simply crashes and needs to be restarted. This is a not very common, but this is quite severe finding in a target, and we have experienced this many times. We send a test case and the target needs to be reset. We had also a case that the target even needed to be reflashed. Protocol fuzzing is also used to identify switching to undefined states. For instance, a target that when a test case, it bypasses the security access mechanisms of the targets, or the response codes are wrong. The target responds with wrong response codes. So those are the typical failures that we can find in general with a protocol fuzzing. And what is the ideal target of a protocol fuzzing? I can have physical ECUs, meaning really an ECU, a vehicle control unit, a motor control unit, a battery management system, or I can also have a virtual ECU. It's very common. We are seeing the market now. Some customers are having a virtual ECU. So before even having the physical setup, I can start fuzzing in a virtual setup. This test can be done in the component level or in a system level, meaning one ECU or several ECUs at the same time. I'm going to deep dive a bit more in the next slides, but this is the concept of the protocol fuzzing. And now we would like to bring also in this webinar for you options that is available in the market to perform fuzzing. So this table, what you're seeing here, we try to consolidate several options for you to think about. Let's start. So what we have here, the first type, open source and proprietary solutions. So when it goes to protocol fuzzing, there are open source and proprietary solutions available. Examples of open source is Bufuzz, Sulay, or AFL. And proprietary solutions, there are several ones available in the market. Ascrypt, CycleFuzz, they are from Intrepid, AutoCrypt, Synopsys, Beyond Security. And there's actually a great list of protocol fuzzes because for automotive industry is quite commonly used. And for source code fuzzing, there are also many options. Open source, there are these options: cluster fuzzing, Radanza, LibFuzzer, Peach Fuzzer, American Fuzz Loop, this AFL that used to be the most common fuzzer until more or less 2017, and then the development was stopped. And then there is a branch available called AFL++ that you can also find open source. And proprietary, we brought two here. There is a company called Code Intelligence. They have a source code fuzzer and also Peach Fuzzer. There is the option of open source and also the paid option. If when to use open source or proprietary, this is a huge discussion. We could stay here hours talking about this. Fact is, there are pros and cons in both approaches. Now, when you consider maintenance, cost of development, long-term maintenance of the tool, or how fast you can bring updates, different customers have different strategies. We've seen also some customers, some people developing in-house fuzzers. So our goal here is to bring these options that you can define your strategy. All right, now I'm going to deep dive a bit more in fuzzing for automotive industry. So when we talk about fuzzing in the automotive industry, black box fuzzing is a technique that is mostly used, more often used at the moment. And one of the reasons, because with a black box testing is the time to test is faster. So yeah, and protocol fuzzing is seen in some literatures. Some literatures state that protocol fuzzing is also one of the most used techniques and a powerful one. But again, depends on our strategy. Just on this topic, we also could stay a couple of time talking here. But when you go for automotive industry, protocol fuzzing, black box testing is the most popular at the moment. And I would like here to deep dive a bit more in the protocol fuzzing and explain some use cases and show a report. How is the anatomy of a report of a protocol fuzzing? So how does it work? In the case of automotive industry, we have here the fuzzer, and we have the targets. The targets can, as I mentioned, can be a physical ECU, can be a virtual ECU, can also be a full vehicle or a hardware in the loop system. And I fuzz these targets through the buses. So it can be CAN, CAN-FT, DOIP, some IP. There are different options today in the market. And how is the architecture itself? What you see in this picture here on the right side, there is a working station, so basically a computer here. And this workstation, there is a fuzzer. So basically what you're seeing here, there are two setups. If we are talking about a virtual fuzzing setup, then everything is running inside the computer, right? So what I have is a fuzzer. This fuzzer is connected to a virtual bus, and the virtual bus is connected to virtual ECUs. Then basically what I have here is a software in the loop setup. Also could be, of course, software open loop, but basically I have virtual ECUs, I have a virtual bus, and my fuzzer is connected to this virtual setup, and I can start fuzzing. Now, may happen also that what I have is a physical setup. In the case of a physical setup, I still have here my workstation with my fuzzer, but then I have outside the workstation, I have an interface to the communication bus. For instance, can be a CAN USB, USB to CAN interface. And then I connect this CAN interface to the physical bus of the target. Can be just one target, as I mentioned, and can be off the physical bus of a vehicle or of a hardware in the loop system. So yeah, this is the anatomy. It's an overview of black box protocol fuzzing, not necessarily black box, because if I have information about the target, it can be gray box. I'll give also another example about it, but that's the anatomy of protocol fuzzing in the automotive industry. And what we have been observed is there are several use cases for the automotive industry. And it's interesting also to see what are the states that we've been observing from the community. So I will start with the most common use case for a protocol fuzzing. So this is the more simple one. And when we talk to the community in the industry or even in conferences that we visit, this is I would say this is the current state more commonly used. What is this state? I have a computer, a bus interface, and a target. Open loop, I connect this target in the bus, and I start fuzzing. So when customers does this, what challenges they are actually wanting to solve? They are wanting to solve the challenge. They have one component, a prototype, ECU, most commonly, and I want to ensure the software robustness and cybersecurity in this ECU, and also be compliant with the ISO 21434. In this case, then to solve this challenge, you can use this physical PC-based tool and a physical ECU. And how this setup looks like, a CAN interface, CAN USB interface, can also be, basic. In general, I have the computer, very simple. I have the computer, the bus interface, the ECU, and I may have or not some information of the ECU. For instance, a black box testing is purely I connect my fuzzer in the CAN bus, for instance, of the ECU, and I start fuzzing. This is a black box test. But if I have some information about the ECU, for instance, the DBC file or the ARXML file, I can also load this information in the fuzzer, and then I would do a protocol fuzzy, but now I would call it a gray box. What are the advantages of this setup? it's very simple to set up. It's really 10 minutes to set it up from the physically, from the physical connections, the wiring harness. I start the fuzzing. I can really have a faster time to initial test. The report analysis is quite simplified, and you can really test in an early stage. Once I heard from a fuzz user, from a person who was using fuzzing, why do they use fuzzing? And the answer was, fuzzing is my way to fail fast. And that's, I think this setup is really shows this use case. You can very fast start testing your hardware. The second use case that we also see in the industry, but not as much as physical setup, but more because the community going in this direction, is also fuzzing with one virtual ECU, but one virtual ECU. What is the challenge here? The challenge are the customers wanting to perform fuzz testing as soon as possible, even before having the physical ECU. And they want to do in a fuzzing in an open loop environment. In this case, the response to this challenge is a fuzzer, a virtual ECU, a virtual bus, running in a simulation middleware, and then and then I start fuzzing. So this is the typical setup. One thing that is very important to notice: if I have a physical ECU, I connect my fuzzing, I start fuzzing and I power the ECU because the software is already running there. In the case of a virtual ECU, I need more components. For instance, a simulation middleware. I need to run the simulation of this virtual ECU. The timing may be different. For instance, that can be slower than real time, faster than real time. So in case you are familiar with virtual ECUs, I can use here virtual ECUs type 2 and 3. There are 4 types of virtual ECUs, from 1 to 4. To perform fuzzing, you need to use VCUs type 2 or 3. That is the virtual ECUs who has the communication layer. The advantage of this setup is that the test can be performed in an early stage before having the physical ECU. And you also can make parallel execution, cloud-based execution, because you don't have the physical setup here. Third use case I would like to bring is also physical ECUs, but in a system level. What is the challenge here? The user or the end user wants to perform fuzzing, but not only in one ECU, but to test the whole system. And then in this case, how to solve this challenge? I can perform fuzzing in a vehicle level, or in a hardware in the loop setup, and I perform fuzzing in multiple ECUs. Some tools allow this, and the typical setup is a network, can be Ethernet, can be CAN. Multiple ECUs can be in a car, also in a hardware in the loop system, in a bench with some ECUs and REST bus. I may have or not the DBC or the ARXML, and I start fuzzing. What are the advantages of this setup is that we can call this as a time efficiency benefit, because you are in the end, you are fuzzing several ECUs at the same time. And you are also testing fuzzing in an environment with a network being more used with several ECUs. So it's a different, so you have the benefits of testing more closer to the final setup, close to a vehicle. And you also have the benefit of testing several ECUs at the same time. So your test run time is also reduced. This we also can see in the industry, some customers doing this, also performing in a system level, in a hardware in the loop, or in a car. And the last use case I would like to bring is the fuzzing multiple ECUs, so several ECUs at the same time in a virtual level. What is the challenge here? I want to do like this fuzzing test, but before having the ECU, or even before having the hardware in the loop or the vehicle. Then I can connect several virtual ECUs in a virtual bus and start fuzzing. A typical setup for this, all ECUs needs to be type 2 and 3. I need a virtual network. I also need a simulation middleware, a fuzzing tool who is compatible with virtual setup, and I run the test. Advantages is that I can do the system level fuzzing in an earlier stage before having the physical issue. Important to say that this setup here, we see customers and we see the community going towards this direction, but I also think it's fair to say that this is not popular yet. It's really, I would say, towards the future. Yeah, this is important, I'd like to notice. And the last part here of my slides before we go to the Q&A, I would like to show when you perform fuzzing, what is the anatomy of a report? In the case of a protocol fuzzing, how do a report looks like? How do a failure looks like? In this case, I would like to show this report here. What we have here is the following. There are 4 blocks. There's 3 blocks here, the test passed, and the 4th, the test failed. What you can see here is the following. I sent a mutated message, and then I sent a request for UDS service, and the ECU said no. And then I sent, so the negative response, and then I sent an instrumentation message. So basically, what I sent was my test case, and then I sent my health check. In this case, the health check, it is UDS service 10 as an instrumentation message. And what I can see here is the ECU responded. I can see +40 here. The ECU responded, so test case check. Then I sent another test case, same thing, another test case, ECU responded. But when I sent this test case here, what happened is that after sending the instrumentation message, there was no response from the ECU. In this case, I keep sending the instrumentation message, there was no response. Then I can conclude that there was a failure. And I can configure this also. When a failure exists, maybe after 3 instrumentation messages without response, maybe after 10, maybe after 1, really depend on your strategy. So this is a typical protocol fuzzing report. And I also would like to bring a test. I used a real use case here that we found in a test. So this use case was the following. There was a certain target. We had the AR.XML file. So we knew basically the CAN messages. And then the first test starting, and one of the strategies was to mutate the arbitration ID, so the ARB ID. So one of the test cases is sent a wrong arbitration ID. What the ECU should do, should reject this mutated ARB ID and keep responsive. What actually happened is that when we sent, we blurred here the ARB ID because of the just confidentiality information, but once we mutated the ARB ID, there was 105 instrumentation requests to the ECUs with no response. And in this case, the ECU needed to be reset. So this was a bug found, real use case that we want to share to you. So with here, I basically conclude more this deep dive in the protocol fuzzing, what a protocol fuzzing is, what are the use cases, and how is the anatomy of a report. And with that said, those are basically the content that we had, me and Thomas, for you. So now we open for questions and answers.